So a ranking vortex is an example we use to illustrate how the viscous stress tensor and the velocity strength tensor works. So it's basically a very idealized version of a vortex. So basically you have a vortex here, and here we call the vortex core, in which the whole fluid just rotates as a solid body. Okay, and on the outside of the vortex core, the velocity decreases to infinity, so that it looks from outside. If you zoom out, it looks just a very thin line of vortex. And if you zoom in, there is a perfectly cylindrical vortex core. So, and the ranking vortex is such that inside the core, so if you draw the velocity versus if you draw the v theta, let's say this is the theta direction as a function of the radius, and let's say a is the radius of the vortex core. So the velocity, in order for the vortex core to be a solid body rotation, the velocity has to increase in what way? It has to increase linearly, right? And then outside the vortex, the circulation around the vortex is fixed. That means the velocity has to decay as what function of r? 1 over r, right? So it decays here to 1 over r. So this is the vorticity field of a ranking vortex. So let's visualize that to see how this looks like. So I'm going to first plot what the velocity field is going to look like. Right, so this is x and y velocity of the ranking vortex flow field. So basically we see a positive velocity above the vortex and the negative velocity beneath it. And also like a positive y velocity left and negative y velocity to the right. So you can see the flow rotates in a vortex. Okay, so if you draw the flow field, it's exactly like what we are looking at here. Can you think about if you look at the velocity strength tensor, how the velocity strength tensor would look like? And ultimately, we are going to get to the example of what is the effect of the velocity strength tensor to the viscous stress, and then how does the viscous stress is going to affect the vortex if there is finite viscosity. All right. So you can think a little bit, and here I'm actually plotting the velocity gradient tensor as a 2x2 matrix, right? Because the whole flow field is 2D. So this is just doing a bunch of math, differentiating this analytical formula. But now if I draw it, this is what I have. dux dx, dux dy. So this is basically the 4 entries of this 2x2 matrix. And you can see now, start to see very interesting things, right? So first of all, inside the vortex core, the diagonal components are what? 0, right? So there is no diagonal components inside the vortex core. And why is that? The vortex core is a solid body rotation, right? And the solid body rotation corresponds to what? Not antisymmetric part of the velocity strength tensor. So the antisymmetric matrix naturally would have 0 diagonal components, right? Because it has to be antisymmetric, right? So this is the first thing we discovered, and there are more things to consider. All right. So this is just the 4 components, and for example, let's extract the rotational component. What should we do to extract the rotational component? We have all these 4 fields, right? So what algebra do we need to do to extract the rotational component of the? Huh? Right, that minus transpose of that. But like if you just look at the flow fields, I mean the rotational components for 2x2 matrix, there is only one number, right? Multiply what by 2? Dx dy by 2. So I think is it David who said it? Who said that transpose multiply add? No, was it, who said that? Okay, yeah. What's your name again? In-Yang. Yeah. Okay. In-Yang said that like you take the matrix, you transpose it, you subtract the transpose, right? So if you do what you said, then if you transpose subtract, the diagonal terms automatically become 0, right? What's left is this minus this, and this minus this, which are opposite to each other. So what we are going to be doing for extracting the rotational component is basically take this and subtract this. And if you just look at these two fields, what do you think we're going to find? Of course, inside the core, this is positive, this is negative. We're going to get a positive rotation. Outside the core, what do you think? It'll be 0, right? Because this looks exactly the same, right? So let's do that. Rotational components, run it. That's the rotation of this ranking vortex. So although all the rotation is inside the vortex core, right? Outside the vortex core, although the flow field looks like it's rotating, it doesn't have any rotating component in the velocity strain tensor. Can anybody make sense of why that is the case? Does it make sense or it doesn't? So who thinks that makes sense? There is no rotation outside the vortex core. You think that makes sense? Okay, good. Can you explain why that makes sense? Okay, so you explain mathematically. That's the case. Yeah, that's right. That's what's carried on. But that's also what is shown by the computer, right? So who thinks it doesn't make sense? It's okay to say like why it doesn't make sense. Right. That's very good. So I think you two have pointed out the key of this issue is that should I define rotation as a global property or local property? In a global way, if you have a fluid element outside of the vortex core, it is rotating around the vortex core, right? But it is not rotating itself, right? So if you have a wooden block, let's say if this is a two-dimensional flow field on a pool, if you put a wooden block over here, if you draw an arrow on the wooden block, you're going to see this wooden block itself is going to be moving around it, but the arrow is always pointing towards the same direction. Okay, it's like the Earth. It's as if like the Earth is moving around the sun, but it doesn't auto-rotate. It's always pointing towards the same direction. Yes. Right. That's another very good analog, right? It's like a Ferris wheel, while the gondola always points hands on the wheel. That's good. Yeah.
Thinking about it, will that be the same what the fluid element inside the core?
Inside the core.
If you put a block of wood there,
yeah,
will it start spinning?
If you put a block of wood here, it'll do two things. It'll go around the core of the vortex, but the arrow, if you have the arrow pointed towards the center, after it rotates for half of the circle, where do you think it will point to? Away? That's actually what happens if you put a block outside. If the arrow is pointing towards the center, then when it goes up there, it'll point away from the center. But if you put a block inside the core, remember, inside the core is like a solid body. Okay? If you have the wooden block sitting inside the core, and it rotates as if it's a solid body with the fluid, then after half of a circle, the arrow is going to point still towards the center, right? Like the whole thing, including the block, rotates as a solid body. So it's like the moon, where one of the faces is always pointing towards Earth as it rotates. If you put the block inside the vortex core. All right, make sense? So this is the rotational component of the velocity strain tensor, and this has nothing to do with viscous stress tensor, right? Okay, so this has no contribution to viscous stress tensor. So what does has contribution is the symmetric part. How many degrees of freedom for this 2x2 matrix does the symmetric part have? 3, right? So let's take a look at them one by one. 2 of them are diagonal, 1 is off diagonal. Okay, so shear component, actually diagonal off diagonal, we plot all of them together. So we have xx, yy, and xy components of the symmetric part of the tensor. So first thing we notice is that inside the core, they are what? 0, right? And does it make sense? I see more people nodding. Why is that? It's a solid body rotation, right? It's a solid body rotation does not have any shear inside it. Okay, and outside, this is what it looks like. So basically, of course, it decays away from the edge of that vortex.